Hey, it's Mr. Lum again, and we're going to do some more electrochemistry, and this time we're going to be looking at calculating how much the initial voltage that a cell can create. Okay, so we have a question here, and it says a cell is made using aluminum metal, 1 molar aluminum nitrate, and lead metal, and 1 molar lead nitrate. So what we see is that we're using 1 molar and 1 molar. We're going to assume that this whole thing is happening at 25 degrees Celsius. So what does that all mean? Well, it just means that everything is happening at standard state. So if everything is happening at standard state, we can use our reduction potentials table. Okay, and I have a little piece of my reduction potentials table here. So we have a couple questions here, and the first question says, draw a diagram and label the diagram. This is always a good idea to do when you have a question, is draw a diagram so you can actually see what is happening. So we're going to draw our electrochemical cell here. So I'm going to draw my 1 beaker and my 2 beakers. Okay, I'm going to draw my salt bridge. So here's my salt bridge. We'll fill it up with some solutions right here. In this solution, I'm going to put in, well, we'll put in the lead one right here. So this will put in PbNO3. Okay, and we'll also put in some Pb metal. So here's our Pb metal. Now on this side we'll put in another type of metal. We'll put in aluminum metal. Okay, so here's our aluminum, Al, and here's our Pb. And in this solution, we'll have AlNO3, aluminum nitrate in this solution. Okay, we're going to attach and connect these 2 electrodes with a wire, so electricity can go through there. There, our diagram is done. Now it does say label here, so we need to figure out which one is the anode, which one's the cathode, which way electrons are moving. So before I finish this question off, we're going to do a redox reaction right here. So here is an excerpt from this, and we see that Pb2 plus is higher up, is a stronger oxidizing agent than Al3 plus, and Al solid is a stronger reducing agent than Pb solid. So what's going to happen is these 2 are going to spontaneously react with one another. So Pb2 plus is going to react with aluminum. So I'm going to write the half reaction for this one, 2 electrons, and that makes Pb. Now aluminum here is going to be on the reactant side. Aluminum solid is on the reactant side, and it's making aluminum 3 plus and 3 electrons. Now I want to put these 2 together, but again, to make the overall redox reaction, I have to make the electrons cancel. So what I'm going to do is I'm going to multiply this by 2 and multiply this one by 3. And that'll make our electrons cancel. Okay, so my overall redox reaction is going to look something like this. It's going to look like timesing this one by 3 is 3 Pb, 2 plus. Now this is going to be 6 electrons, and this one's going to be 6 electrons, so therefore they're going to cancel out. And so this one's going to be plus 2 aluminum, solids, and that makes Pb solid, 3 Pb solid, 3 Pb solid, and 2 aluminum, aqueous. Okay, and now this is our balanced reaction right here. Now, again, this one is gaining 2 electrons, and aluminum right here is losing electrons. So aluminum is losing electrons, and if you remember, LEOA, or losing electrons, is oxidation and is the anode. So that means since aluminum right here is losing electrons, this is the anode. This one is gaining electrons, Pb2+ is turning into Pb solid, so it's gaining electrons, and therefore this is the cathode. And this one's losing electrons, so electrons are leaving, and they're moving towards cathode. Electrons move from anode to cathode. Okay? Now, the next question, so here's our finished diagram. We've labeled it, we've drawn the direction, the direction of the flow of electrons, we've labeled anode and cathode. Here's our salt bridge. I probably should say what's in the salt bridge. You can pick pretty much any salt. Since we have NO3 here and NO3 here, and I want to make sure that nothing reacts in our salt bridge, I'm going to pick something that's kind of non-reactive. I'm going to pick KNO3. Okay, and I'm going to put that in my salt bridge right here. Okay, so it's very, very soluble. It's not going to form a precipitate with Pb or with aluminum right here. So it's a good choice for a salt bridge right here. Now, my next question, it says, calculate the initial cell voltage. So what I'm going to do is I look at the reduction potentials of these ones. Now, if I just, what I can do is I can go cathode minus anode. So a formula you can just memorize right here is cathode minus anode equals your cell voltage. Okay, and what we can say is your E naught cell. That's your not initial, your initial cell voltage, or the initial energy of your cell, and we just go cathode minus anode. Okay, which is this right here. So we can go cathode. Now which one's our cathode? Let's find out. Pb is our cathode. So what we're going to do is we're going to go minus, we're taking it right from the table, minus 0.13 minus our anode. So minus our anode. And our anode is this aluminum one here. So we find aluminum and we just put in this number right here, minus 1.66. And what we see is that E naught cell equals, well, 1.53. Remember, since this is two negatives, they're going to turn to a positive, and so this turns into positive 1.53 volts is the initial cell voltage, and this is the final answer. Now, remember, what is this reduction potentials table all about? It's about differences. So what is the difference between these two right here? So the difference between negative 0.13 and negative 1.66 is, the difference is 1.53 volts. That is the difference. Okay. Some people use a different method. Some people take this and they know that this is a different sign because they're flipping it around, but this is a formula that always works for everything. E naught cell equals cathode minus anode. And so you can just type this in. And what it is just we're measuring just the reduction potential differences, the difference between these two numbers, and that is our initial cell voltage. Or you can just memorize this formula, E naught cell equals cathode minus anode. Okay. Now, here's an important thing that some students kind of get messed up on. They see this. They see PB was times by 3. And aluminum was times by 2. So some students want to take these numbers and they want to times them by 3 and times by 2. Remember what the definition of voltage is. Voltage means the amount of work done per electron. Okay, so even though we're multiplying the electrons, so for this one we have a total of 6 electrons, we're multiplying the electrons by 6. No, it's the amount of work done for each electron. And each electron is doing 1.53 volts of work. So you can be multiplying by however many you want, but each electron is only doing this amount of work. Okay? So even though you multiply up here, you do not multiply down here. Let's move on. So here's another question. Calculate the potential for this reaction right here. Okay. So it says we can just use our trusted formula of E naught cell equals cathode minus anode. Now, so which one is our cathode? Remember these little acronyms kind of things, GERC and LEOA, or LEO. So gaining electrons is reduction, and that's the cathode. So which one is gaining electrons? Let's try to figure that out. So gaining electrons is, well, this one seems to be gaining. It's 2 positive, and then it becomes right like this. So if you looked at your oxidation numbers, this has an oxidation number of 2 plus, and this has an oxidation number of 0. And if you go in this direction, what we can see is that the oxidation number decreases. So this is your site of reduction. This is reduction. It gains electrons, therefore it is reduction, therefore it is the cathode. This one goes from an oxidation number of 0 to 2 plus. Therefore the oxidation number increases. Therefore it loses 2 electrons. Losing electrons is oxidation, and it's the anode. So what we're going to do is we're going to do cathode minus anode, or we're going to go this one. So E naught cell, cathode, which is CO2 plus, cathode, minus 0.28 minus anode. Okay, so this one is oxidation, nickel is oxidation, minus 0.26. Okay, and our E naught cell equals, oh, now this is interesting, minus 0.02. Last time we had a positive number. Now a positive number meant that it is producing that much electricity, that many volts per electron. Now this one says negative number. So what does that mean? Well, a negative number means that this reaction is not spontaneous. Okay, so again, this is a non-spontaneous reaction. And that makes sense too. Like, look at what we have here. We have nickel, solid, reacting with cobalt. Our line is going in this direction. This is our spontaneous way. This is the non-spontaneous way. And we get a negative number. So anytime you take E0 cell and you get a positive number, it is a spontaneous reaction. Spontaneous reaction. That means it is going to make electricity. Now when you get E0 cell equaling a negative number, it is non-spontaneous. Now, what it means is this reaction can happen. However, you have to add electricity. You must add electricity into it. It will not happen by itself. You have to add electricity. Okay? And that's going to be our starting point for our next section, which is going to, we're going to talk a little bit later on about the electrolytic cell. So the electrolytic cell, we have to add electricity, and for the electrochemical cell, it makes electricity for us. Okay, so again, negative number, non-spontaneous. Our last example was a positive number, so therefore it's spontaneous.